Okay, so we're going to go over the last two periodic trends, electron affinity and electronegativity. These are fairly similar ideas, but there's some subtle but important differences that I'll try to highlight, okay? So the electron affinity is the energy change associated with adding an electron to a gaseous atom. So it's how exothermic this process is. This is basically the exact opposite of ionization energy, right? Where we were removing an electron in the gaseous state to form a cation. Now we are adding an electron in the gaseous state to form an anion. And you can see here's kind of a plot of the different electron affinities. We usually only talk about the first electron affinity, although in principle you could do the second electron affinity. It's just difficult to measure, it turns out. And so you'll notice some things here, right? Look at radon, okay? Radon basically has a zero energy given off when you form this anion. Why is that? Well, radon's a noble gas, right? Radon already has a stable electron configuration, so it doesn't want to gain any more electrons. Adding that electron is adding an electron to a higher level orbital that's in a higher principal quantum number, okay? So you'll notice all the noble gases are basically zero. So helium, neon, argon, krypton, and xenon, and radon, okay? You'll also notice that the halogens, right next to the noble gases, they really want that one electron to become like a noble gas, to become like the noble gas configuration. So fluorine, chlorine, bromine, iodine, astatine, those are very exothermic so they have very high electron affinities to form that -1 ion. Okay, and then there's also some ones in between that look to be close to zero, and that has to do with half-filled shells. So if you look at a periodic table, let's go back to a periodic table here. Manganese, Mn, that was close to zero, and so there is manganese. Manganese has a half-filled 3d orbital, okay? What do I mean by that? Well, what's the electron configuration? It's going to be bracket argon, 4s2, that gets you to calcium, and that's going to be 3d, 1, 2, 3, 4, 5, okay? So that's going to be halfway filled to the 3d orbital because the d orbital can hold up to 10 electrons. You have 5 different orbitals, right? Principal quantum L values, angular momentum, quantum M sub L values, orientation quantum numbers are going to be -2, -1, 0, 1, and 2. 5 different d orbitals. And when you have a half-filled a shell like this, D shell, or any type of shell, that's a stable configuration. Because now you have seats on the bus rule, Hund's rule, you have 1 electron in all 5 of those orbitals. And so manganese doesn't really want another electron because it's going to have to put it next to another paired orbital. So just to be really clear about what I mean there, let me just draw that out for you. So we're talking about manganese and why manganese has an electron affinity pretty close to zero. And it has to do with its filled half shell. So if we wrote, okay, 3D, we're going to be bracket argon, we said, right? And then we're going to have 4s2. And so if we draw our orbital diagram, that'd be spin up, spin down. And then we have 5 d orbitals, as we know from our electron configuration and quantum chemistry chapter. And with manganese, they're all going to be spin up or all going to be spin down. It's arbitrary which way you put it. But Hund's rule, seats on the bus rule, tells you that they're going to occupy different suborbitals, different subshells. And so that's pretty stable. Manganese doesn't really want to become D6 like iron, which is next on the periodic table. See, that's iron. Because then it has to pair, okay? And it has to put an electron really close to another electron in the same subshell. It's not going to be unfavorable. That's going to be unfavorable. So a lot of these ones with half-filled shells are going to be pretty low electron affinities. The same thing is true for nitrogen, okay? So if you look at where nitrogen is on the periodic table, nitrogen is in the middle of the P's, right? It has a electron configuration of bracket helium, 2s2, 2p3, half filled p orbital, 2p orbital. P orbital can fill 6 electrons. So same reason. It's not going to want to add that 4th electron too much to become spin paired. All right, so that explains some of the general things about electron affinity. Electronegativity is very similar to electron affinity. It has to do with gaining electrons, but it's within a compound. So it's always in the context of a compound. We talk about the individual electronegativities of an element, but it's always measured in a compound. Actually, this is how it's measured. It's in a set of a compounds, okay? And so it's basically how much elements want electrons, how much of a tug of war is there? Is it going to win the tug of war versus another element? Or is it going to lose the tug of war? Okay. And we'll see this actually describes in the next chapter a lot about what types of bonds are made, whether or not you have an ionic bond and you gave up an electron or gained an electron and made an ion, or you have a covalent bond where you're sharing electrons. If you have similar electronegativity, you can share electrons. If you have drastically different electronegativities and one atom partner is much stronger at pulling away an electron, you're going to form ions, right? You're going to gain and lose electrons. And so the trends are that the electronegativity increases across the periodic table and decreases going down the periodic table. And this has to do with nuclear charge and distance of the electron from the nucleus. So if we're increasing across the periodic table and decreasing down the periodic table, then, well, the top right is going to have the highest electronegativity. Fluorine is at the top right of the periodic table, okay? Helium looks like it's at the top right, okay, but helium's a noble gas, so that doesn't count, okay? Noble gases can't form compounds, so you can't talk about electronegativity for noble gases. Fluorine is the top rightmost element that isn't a noble gas, hence it has the highest electronegativity. These 4, nitrogen, oxygen, fluorine, chlorine, have the highest electronegativities known. They want to fill their orbitals by whatever means necessary. They want to gain electrons when they're with a compound. So there's the scale that's used varies between 0.7 and 4. You know, you might think that's kind of weird. Why? Linus Pauling calculated it this way. I guess he could have changed the numbers to whatever he wanted, but it's just what everybody uses now. So we go from 0.7 to 4. So you notice, yeah, fluorine's the top right. It's 4. It's the highest. Bottom left, francium. That's decreasing electronegativity going down, increasing electronegativity going right. Francium and cesium are both 0.7. So very electropositive, you could say, or very low electronegativities. And so this is how Linus Pauling calculated it. I don't really want you to worry about this too much, but if you're curious, you can see this formula. He basically looked at compounds mostly with hydrogen is where he started with, and X is just some generic element that he's measuring the electronegativity of. And he looked at the bond energy, and you would expect, right, if you had an equal sharing of electrons, equal electronegativity, you'd expect that the bond energy would just be that of a hydrogen molecule, HH. Bond energy would be an average between an HH and a dimer, okay, a diatomic version of that element that you're measuring. It would just be the average. Those two bond energies divided by 2. But you'll see that that's not actually true if you look at the experimental data. And so he just took that calculated expected bond energy, for equal sharing, and then subtracted from it what you actually measure. And that gave you some idea of, you know, how much electrons are being pulled from one to another. And so that's pretty much it for this whole chapter, guys. A pretty short chapter. You just got to know your periodic trends and also know the rationale why things are changing the way they are. Okay? We'll see you on the next chapter.